Okay, uh, hello, namaste, and welcome everyone. Welcome to this problem solving session. Sorry, we are starting 30 minutes late uh, because of some issues from my side. So maybe we'll get started directly. Okay, just a second. Let me set up the recording. I hope I am audible. Right? Uh, okay, thank you. So let me share my screen on the recording. Okay, all right. So I think we can start. Okay, so this is uh, week 11, right? Okay, so this is week 11, and the main focus of this week has been two things basically. First is statistical hypothesis testing, right? And there is one uh, important result as well, which is Neiman Pearson lemma, right? So this week basically focused on these two things. Uh, I'll give some intro to these things and then we'll solve some problems. Okay. So what is basically hypothesis testing? Let's start with hypothesis testing. Hypothesis testing. Right. So hypothesis testing is basically, so what is a hypothesis? Hypothesis is something which, so it's hypothesis is basically a claim, right? So I don't remember the exact definition of hypothesis, but it's a claim. Okay. It's a claim about an unknown parameter. Well, it's a educated claim, right? It should be an educated claim, meaning you cannot just say anything. I mean, one could claim anything, right? But it should be an educated claim. You should have some evidence for that claim, right? Anything, so any educated guess or and a claim on some unknown parameter, you can call that as a hypothesis. Okay, so people keep hypothesizing a lot of things, right? I mean, there are a lot of things that one can hypothesize. For example, one can hypothesize that uh, uh, India will become uh, you know a 5 trillion economy. So it's a hypothesis. It hasn't happened yet, but we are hypothesizing it because we have evidence for it, right? These kind of claims, these are hypotheses. Or for example, you see hypothesis in a lot of things, right? For example, even in machine learning, you keep seeing a lot of hypotheses. For example, if your model or whatever AI model that you are using is, let's say, not working properly or it's giving some random values, you hypothesize why it is not working, right? So these are all like educated guess or educated claims on something which we don't know, basically, right? So that is what hypothesis is. And what is hypothesis testing then? Well, hypothesis testing is just, you have multiple hypotheses. Okay. For example, I have one hypothesis, you have another hypothesis. So the question then arises is like, whose hypothesis is better? Okay. So when these kind of questions come, that is what we call hypothesis testing, right? So, so that is what hypothesis is, and what is hypothesis testing? Hypothesis testing is basically check checking which hypothesis is more likely. Okay. So, I mean, if we go back to our like that India example, like if I claim that, India won't become a 5 trillion economy, and you claim that, well, India will become a 5 trillion economy. Well, the hypothesis testing will basically answer whether my hypothesis is more likely to happen or your hypothesis is more likely to happen. And then, I mean, you can see the past data, come up with some rules and then say, well, the hypothesis that India will become a 5 trillion economy is more likely to happen, and hence that hypothesis is more correct in some sense. Okay. So this is what hypothesis testing is in a nutshell. Okay. Um, okay. If that is clear to you, then so what is statistical hypothesis testing? So in statistics, the hypothesis testing has a particular framework. So I mean there are multiple frameworks for hypothesis testing, but the one that we are going to follow is a binary hypothesis testing. Okay. So what is it? So 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 maybe I will just write it down. So what is statistical hypothesis testing? What is that? So basically, so formally, uh, we have two hypotheses, right? Two hypotheses. Yes, I think, yeah. So the first hypothesis is what we call as the null hypothesis, right? H naught. We denote it by H naught, and what is that? This is called the null hypothesis, right? Uh, uh, which representing, sorry, representing what? Representing the uh, status quo, right? Status quo on or default assumption, right? So, so H naught is so the null hypothesis is basically something that which you assume by default. For example, let's think about let's consider a concrete example. Let's consider a drug trial example basically. Okay. So let's say that you are in a medical lab, and you are testing different drugs for let's say cancer. Okay, or any particular any disease, okay, for that matter, and basically you want to come up with some drug which will cure cancer. Okay, now since you know that it's difficult to come up with a drug that you know cures cancer. I mean there have been some recent claims that, yeah, but I mean till now there's not a lot of evidence for that, but yeah, by default you will assume that okay, any particular drug that you're testing will not be effective against cancer. Okay, that will be your default assumption, right? So that is your null hypothesis. However, let's say, I mean, so it is basically something that is that has happened in past, and you are basically, taking that as a result for the next experiment as well. Okay, so I mean, yeah, this drug example works the best for me. So you have a lot of drugs. You are trying a lot of drugs and none of them are working. So you whenever you're trying new drug, you think that most probably this drug will also not work. So that is your null hypothesis. Okay. So this is your null hypothesis, right? And the second hypothesis, which you call H1, is this is called the alternative hypothesis. The alternative hypothesis. Okay. So what is this? This representing representing a specific deviation from null hypothesis. Right? So again, if we go back to our drug example, you're trying a new drug. H0 was your null hypothesis, right? That the drug won't work. Okay. But there can, so these are all hypotheses, right? It's a educated claim. Now one can also hypothesize that, well, this drug will work. Okay. So you are testing a drug. The null hypothesis or the default assumption is that this drug won't work. However, there is another alternate hypothesis that okay, this drug will work. Okay. That is your H1 basically. Okay. So I mean, you see, like H0 is something basically that has happened, and you have some confidence on H0. And H1 is like, okay, uh, well, it's not necessary that what has happened in past will happen again. So it's a deviation from what has happened in past. Okay, in some sense, I'm just giving you a very crude explanation here, but yeah, I hope the message is clear, right? So these are the so in statistical hypothesis, the framework that we are going to consider, these are the two hypotheses that we will be working with, right? So you will have a null hypothesis and an alternative hypothesis. And so the question that basically comes up is that, is the should so the question is always like this, H naught is since H naught is your null hypothesis or your default assumption, the question always revolves around, well, should we accept the null hypothesis or should we reject the null hypothesis? That's the basic question that you will always try to answer. And one may ask, okay, why are we so concerned with the null hypothesis? Well, it's simply for the fact that, null hypothesis is something that has some weight to it in the sense that it has happened in past, or, it's default assumption basically. And if you want to reject the default assumption, you have to have some concrete proof for it. So that is why in hypothesis testing problems, you will always find that things are revolving around the null hypothesis. Okay, so I mean, if that is very, very clear to you, there are two things, two properties, or two uh, sort of uh, concepts that are relevant to hypothesis testing. Okay, so maybe I will write them down. So like maybe how do I say it? Maybe I will write it down. Okay? So there are two things. So first is called the type 1 error. Maybe I'll write it like this. Okay? I'll make a table. Type 1 error. Okay. The other one is type 2 error. Type 2. People also write it like this. Type 2 error. This is also called your false positive. Okay? And type 2 error is also called false negative. Okay. So what are these things? So first of all, definition wise, type 1 error, this occurs. when we when we reject a null hypothesis, maybe when we reject H naught, the null hypothesis, right? That is actually true. That is actually true. Okay. So, in other words, we conclude that there is a significant effect or difference when there is none in reality, right? I mean, so there is a default assumption, and you're saying that, well, this default assumption is not true, when actually in reality the default assumption is true. Okay, so that is why you call it false positive. So the null hypothesis is actually positive in the sense it's true. However, you are saying that it's false. Okay, this is what we mean by false positive. Similarly, type 2 error occurs when we fail to reject a null hypothesis. When we fail to reject a null hypothesis, that is actually false. That is actually false. So, in other words, we fail to detect a significant effect or difference when there is one in reality. I mean, so let's say, so it's like, you are saying that, the default assumption or your null hypothesis is actually true. You're saying that it's true. However, in reality, it's actually false. Okay. So so I hope, so it's like, uh, so it's like saying that, the null hypothesis is actually negative, meaning it's false. However, you're saying that, it's true. So it's false negative, right? I mean, uh, so it's like you are accepting it, hence, so you're saying you are accepting the null hypothesis. However, in reality, it's actually false. That is why the name false negative, right? So, so these are type 1 and like type 2 error, right? And so there are some conventions related to these things. I will just note those down. So here is one. So this is denoted by alpha, right? Okay. Uh, so it denotes the significance level, significance level, or the probability of making type 1 error, right? So it is basically the probability of, rejecting the null hypothesis when it is actually true. So what is the probability of type 1 error? That is denoted by alpha. Similarly here, it is denoted by beta, type 2 errors, right? Beta, uh, it denotes the probability of making a type 2 error, right? So it is basically the probability of accepting the null hypothesis when actually it is false. In reality, it is false, right? And a last point that I would like to add here, just for like the sake of like clarity and uh, so that we are clear about these type 1 and type 2 errors, is an example, right? So in a clinical trial, a type 1 error, when will a type 1 error happen, right? So the drug example that I just gave you. So type 1 error will happen if we mistakenly conclude that a new drug that a new drug is effective, a new drug is effective. So this is so it's like rejecting the null hypothesis. The null hypothesis is basically that the drug is not effective, but you're saying that it's effective. So you're rejecting the null hypothesis, right? When it actually has no effect, right? So this is like a type 1 error in a clinical trial, right? Similarly, when will a type 2 error happen in a clinical trial? It will happen if 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 we fail to conclude that a new drug, if we fail to conclude that a new drug uh, is effective. So this is like accepting the null hypothesis, right? We are saying that this new drug is not effective, right? That is what our default assumption is, right? So we fail to conclude that it's effective. That means that we are accepting that it's not effective when it actually has a beneficial beneficial effect, right? So so I hope this example makes it very concrete, right? That what is type 1 error and what is the type 2 error. Okay, so in general, uh, okay, so I mean, see, in general, so there is no like concrete answer, okay. But in general, type 2 error is like more dangerous, okay. So when you say that you're actually doing a type 2 error, that is actually more dangerous basically. So so I mean, so for example, in this case, right, let's say that there was a drug, okay, and it was actually effective, and you're saying that it's not effective. So in some sense, that will cost you more, right? I mean, it's like you are missing out on some opportunity here, right? Right. So yeah. Uh, okay. Right. So okay. Okay. Uh, yeah. So I have defined this. Maybe I'll just state the NP lemma, right? Name and Pearson lemma, and then we can go. So I mean, just I will just mention that, and then we can start. So I was just thinking on your question that which error is actually more dangerous. So for example, when deciding whether a new drug has any positive effect on patients, right? Default belief will be that most medicines have no effect, right? That is your null hypothesis. And we will require overwhelming evidence that most medicines have no effect. So to believe that some medicine has some effect, you will need like some more evidence, right? So yeah, uh, right. So yeah, I think yeah. I mean, I think it varies from like situation to situation. However, yeah, falsely, I think rejecting, right? So in most cases, false positive would be more harmful, right, than false negative. Hmm. I think I answered your question incorrectly. So I think false positive, right, that is more dangerous because think about it. So I'm sorry, right? I think type 1 error are more dangerous, right? Because so let's say there is some drug, okay, and you mistakenly say that this drug is actually effective. However, in reality, it wasn't effective. That is actually much more harmful, right? Because now the patients will take something that is not effective at all, and you know they will assume that it's actually effective. That is more dangerous as compared to the situation where you have actually concluded that it's not effective. However, it was actually effective. I mean, type 2 errors are like missed opportunities, but type 1 errors are like doing some blunderous things. So I think type 1 error is actually more harmful compared to type 2 error. Okay. So yeah, I think so to answer your question, I think type 1 errors are more dangerous compared to type 2 errors. So now maybe I will just write like mention few definitions. The first is the power function. Power function. So it is denoted by like beta of theta, right? Beta of theta. How what is it? It is the probability under theta, right? To reject H naught, right? So it's basically the probability of rejecting the null hypothesis for a given theta, right? The next thing is what? The next thing is uniformly most powerful cells. Right? Uniformly most powerful cells. So what is this? So uh, so okay, a hypothesis. So let's say that there are a class of tests. So there is a class of tests. Let's denote it by this calligraphic T. Okay. So you say that in this class of tests, a particular hypothesis test with power beta is uniformly most powerful if it has higher power than all other tests in that class. Okay, so this is how you define the power of a hypothesis, and there are a class of tests. Okay, and you say that a particular test T is the most powerful it is if the power of that test is greater than all the power for the test in this class T, right? So formally speaking, so uh, so if beta of theta, right? So the power of a particular hypothesis test is greater than or equal to beta tilde of theta, right? For all theta. So sorry. No, so power is just a property of a test, right? I mean, it is just that, under this parameter or under this hypothesis, what is the probability that I can reject the hypothesis, null hypothesis? Okay. So it's like a property uh, of a test, right? So every test has a power. So basically, I mean, intuitively speaking, it's like saying that, uh, so if a test has more power, it means that it has more evidence to reject the null hypothesis, right? I is it clear or should I repeat? So if a test has more power, it means that it has more evidence that the null hypothesis is not true. I don't know if it is clear or it's for rejection, only for rejection, right? So and so if you are given a class of test T, then the most powerful test is the one which has the which has the highest power. In some sense, it is like saying that in this given class of test, this particular hypothesis gives me the most powerful evidence to reject the null hypothesis, and hence it's the most powerful test. Okay, okay, and then there is the definition of size, right? So what is size? So the size of a hypothesis test is basically the probability of incorrectly rejecting the null hypothesis. Okay. So okay, maybe I should write here theta one. So theta one is like your alternate hypothesis, right? Uh, and size is basically uh, what it's the probability of incorrectly rejecting the null hypothesis. So it's defined. How will you define it? It's like supremum of theta belonging to theta naught, right? Theta why theta naught? Because you are now working under the null hypothesis, right? So you are rejecting the null hypothesis, and this is the probability to reject x naught, right? So this is probability under theta. So you see all the thetas under the null hypothesis, okay? And then what is the probability that what is the probability of rejecting the null hypothesis, okay? And you take the supremum of that, that is your size, okay? And the last definition is that of a level, right? What is the level? The uh, level alpha, sorry, level alpha uh, falsely, so it falsely rejects at most alpha fraction of the time. So, mathematically speaking, what is it? So, it's like supremum of theta belonging to some theta naught probability of reject h naught is less than equal to alpha. So, this is what alpha level is. Okay. Okay. So, the level of a hypothesis test is defined as follows. Okay. So, if all of this is known, then the last thing that we will do and like we start solving problem is a Neyman Pearson lemma, right? What is it? So you have your h naught that is theta is equal to theta naught. So your parameter is theta naught, and there is an alternate hypothesis which says that theta is equal to theta one. Okay. So the Neyman Pearson lemma says that the most powerful test among alpha level tests, right? So it's like you are fix the level. Okay, so you are fixing some level, right? So you are basically saying, the type 1 error has to be fixed at alpha. Okay. Fix level alpha. So the level is fixed. Okay. So now you are considering all the tests that has alpha level. Okay. And you say that says uh, that a test is uniformly most powerful full test among alpha level tests if it rejects H naught if and only if fx of x theta 1, so the likelihood under theta 1 divided by likelihood under theta naught, right? This is greater than some con uh, scalar kappa for some kappa that belongs to some real number. Okay. And what is this kappa? Kappa is basically this thing. It's this thing. So probability under theta naught. So alpha is a probability under theta naught. F x x theta 1 by f x theta 2 greater than kappa. So if under theta naught, okay, if under theta naught, this likelihood ratio is great. The probability of this likelihood to be greater than kappa, if that is equal to alpha, then uh, a test, okay, and the alternative test is the most powerful, okay, if this likelihood is greater than kappa. Sorry, kappa. Yeah, it's constant and it has to satisfy. Yeah, it is a constant and it has to satisfy this property. Sorry. Yeah, it has a constant value, but it has to satisfy this thing as well. I mean, you basically determine kappa using this thing. Okay. First you determine kappa using this thing and then use this kappa here. So this is your Neyman-Pearson lemma, and it basically what is it telling you is that the likelihood ratio test is the most powerful test. That's it. Okay. Uh, okay. So let's start with some few problems that I have for this thing. So if you have some question, you can ask. Maybe I will just have some drink. I will drink something to just because I've been speaking for some long time. Okay. Okay. If there are no questions, then we will start with solving some problems. Okay. So these things are first. Maybe I'll start. The first problem. So it's given that you have two probability mass functions f0 and f1. So these are two PMFs. Just a second, give me some second. Is there something? Um, okay. So f0 and f1 are two PMFs, probability mass functions, right? And you are given some table for it. So what is the so these PMFs are given to you. So you have x, you have f0 of x, and you have f1 of x, right? So what are the values that x can take? It's a mass function, so the values are discrete, right? So it's 0, 1, 2, 3, 4, 5, right? And the value of f0 for 0 is 0.5, so 0.1, this is again 0.1, 0.1, 0.1, and again 0.1. So just check if this sums to be to 1. Yeah, it sums to 1, okay? So this is 0, so f1, this new another PMF is 0.1, 0.1, 0.1, 0.2, 0.2, 0.3. is 0.3, 0.3, 0.6, and 4, 10. So these are the two these things, right? Consider the problem of this testing of the null hypothesis. So H naught is your null hypothesis that X comes from F naught, okay? Against H1, which says that X comes from F1, based on where X, X is a single observation. Single observation. Okay. So you have then alpha is your size, right? And beta is your power, okay, of the test. With and this test has a critical region of x such x in R such that x is greater than 2. What is the value of 10 times alpha plus beta? Okay, so basically you see one observation of for this random variable x, right? And you have two hypotheses that x comes from f naught, which is your null hypothesis, and x comes from f1, which is your alternate hypothesis. Uh, it is given to you that alpha is your size and beta is your power. Okay, we just saw what is the meaning of size and power. Okay, and this is the critical region, right? Uh, so if x is greater than 2, you reject the null hypothesis. If x is less than 2, you accept the null hypothesis, right? So this is your critical region. And the question is, what is the value of 10 times alpha plus beta? What is this value, right? So, so it is simple. So the size is basically your type 1 error, right? So alpha, so let's see the answer. The alpha is equal to probability under H naught, right? When will you reject the null hypothesis? If x is greater than 2, right? This thing. So under H naught, which is your that x, the H naught is basically that x is coming from H naught, right? So under F naught, what is the probability that x is greater than 2? So it's these three things, right? X is equal to 3, x is equal to 4, and x is equal to 5, right? And what are the probabilities? Zero point 0.1, zero point 0.1, and zero point 0.1. So this is zero point 0.1 plus zero point 0.1 plus zero point 0.1, which is equal to 0.3. So the value of alpha is 0.3. And similarly, what is beta? So beta is basically the probability of rejecting the null hypothesis under the alternate hypothesis plus, right? So this is the probability. When will you reject the null hypothesis? When x is greater than 2. However, this time the probability is under the alternative hypothesis. Now under H1, x is coming from F1, right? F1. What is the probability of x is greater than 2? 0.2 point, so x should be equal to 0.3, which is 0.2. Probability of x equal to zero point 0.4, which is 0.2, and probability of x equal to 5, which is 0.3. So you just sum all these, so it will become zero point 0.2 plus 0.2 plus 0.3. What is this value? This is 0.7, right? So this is the value of beta. Now, simply what is the value of 10 times alpha plus beta then? So this is 10 times zero point 0.3 plus zero point 0.7, which is 1, is equal to 10. This is your answer, right? A simple example, simple problem, in fact, right? Okay. Any question? Uh, just just to make sure that okay. No question? Okay. We'll move to the next question then. Lot of heat nowadays in Bangalore. It's important to keep yourself hydrated. Let's look at another question. Uh, yeah. So the next question is that X is basically a single observation that you draw from uniform 0 comma theta. Okay, and so it's a uniform random variable with parameter of the distribution 0 comma theta, and theta can actually assume value, theta can assume only two values, right? So can either assume the value 1 or it can assume the value 2. That's all. So now you have h naught, which is theta is equal to 1, which is your null hypothesis. And then you have your alternate hypothesis, which is theta is equal to 2. Okay. So now your the test procedure to reject the null hypothesis is as follows. So it says that reject H naught if and only if and only. So if I write double F, it means if and only if, right? If and only if X is greater than 0.8, right? So alpha is your probability of type 1 error and beta is probability of type 2 error, right? Then what is the value of alpha and beta? This is the question. So again, a simple question. So what is the probability alpha? So it's the probability under H naught that you are rejecting the null hypothesis. When will you reject the null hypothesis? When X is greater than zero point 0.8. X is greater than 0.8, right? Now, what is H naught? H naught says that theta is equal to 1, right? So it's basically probability under theta equal to 1, x greater than 0.8, right? Now, what is this probability? So theta equal 1, probability x greater than 0.8. So, I mean, so it's a uniform distribution, right? Uh, so it's simply what? Integral x greater than zero point 0.8, so it will go from zero point 0.8 to 1, right? And what will be the probability? 1 times dx. That's all, right? This is your probability. So basically, you're just integrating the probabilities, right? That's all. So what will that be? This will become 1 minus 0 0.8, which is what? 0.2. That's all, right? So that is the value of alpha. Similarly, what is the value of beta? So it's the probability under H1 of rejecting the uh, okay, so this is type 2 error, right? Uh, right, so it's the probability under H1. So what was type 2 error? Just recall the format, the definition. It is the probability to fail to reject the null hypothesis that is actually false. Okay, so when will you, if you fail to reject the null hypothesis, that means that you are accepting the null hypothesis. And when will you accept the null hypothesis? When this condition is not satisfied. That means that if x is less than or equal to 0.8, right? This is your type 2 error, right? So this is actually 1 minus probability under h1 that x is greater than 0.8, right? So it's like 1 minus probability of a complement, and that is 1 minus probability theta equal to 2, x greater than 0.8. What will this be? 1 minus integral 0.8 to 2, right? And what 1 by 2 dx, right? This will become 1 minus 2 minus 0.8 by 2, right? This thing is 2 minus zero point 0.8 is 1.2 by 2 is 0.6. 1 minus zero point 0.6 is 0.4. So yeah, so you have your answer here, right? That alpha is equal to 0.2 and beta is equal to 0.4. This is your answer. Okay. Anything not clear? It seems that everything is clear. So let's move on to the next question. Which question should I take next? Okay, maybe this question looks good. Okay, so it's a lot of heat actually. Let me drink some. You keep drinking after a question. So stay hydrated. Okay. So this is the third question. So okay, this is what it is. So there's a coin. There's a coin tossed four times, right? And P, sorry, not beta. P is the probability of getting heads. Okay, in so in each one. So it's a biased coin, right? Uh, so okay, I mean we don't know if it is biased or not, but yeah, this is the probability of getting heads if you toss the coin. So and S is the number of heads obtained. Number of heads obtained, right? So it is two. So the two hypotheses are as follows. H naught, which says that P is equal to half. Okay, so this is like saying that the coin is unbiased, right? That is a null hypothesis. Okay, because ideally you would assume that a coin is unbiased. So this is your null hypothesis or default assumption, and you have an alternative hypothesis which says that P is not equal to half. Okay, now you have the test function for this thing. To check is basically phi of s. So s is the number of heads that you see, right? This thing is equal to 1. Uh, right. So if this is 1, if s is equal to 0 or s is equal to 4. Okay. So if you're tossing the coin four times, you can see the heads at least 0 times or at most 4 times, right? So if the value of this is 1 if s is equal to 0 or s is equal to 4. Its value is p naught if s is equal to 1 or s is equal to 3, and it is 0 if s is equal to 2. And so you reject h naught if phi of s, right? Phi of s is greater than 0. So if you see that that the number of heads in the four tosses is not equal to 2, then you say that, well, you know uh, the null hypothesis is not true, and hence the coin is actually biased. So this is clear to you. What is the solution? Solution is quite simple. So let's say that xi is the random. So it's the random variable associated with ith toss, right? And you have been given that so x1, x2, x4, all of these are coming from IID. So since this is a coin toss, right? So it's a binomial. I mean, individually you can also say that they're Bernoulli, but I mean, a simple way to look at it is binomial with one trial and probability of success p, right? So if so s is the number of heads, right? So I mean, how will you write s in terms of x1 to x4? It's quite simple, right? So let's say if you denote that the heads is denoted by 1, right? Then actually s is nothing but summation of xi I equal to 1 to 4. So if there are three heads that have come, then there will be three ones here in x1 to x4, and the summation of these will be 3 because the another will be 0, right? Now, since S is like summation of IID binomial random variables, this summation of IID binomial is again binomial, right? With what? With the number of trials equal to 4 because you are adding four uh, you are adding uh, four terms, right? Four IID binomial random variables, and the probability of success will still be p. So this is now convenient, right? So we know the distribution of this thing and we know the distribution of this thing. Fine. Now, what is the type 1 error, right? Okay. Well, now it is given. Okay, so, okay, the question, I didn't actually tell you what the question is. The question is that it is given that alpha, which is equal to probability of type 1 error, this is given to you to be 0.25. Okay, this is given to you to be 0.25. The question is, what is the value of P naught? So if you remember, P naught is this thing, right? The you are given the probability of type 1 error, so you are given the value of alpha. The question is, what is the value of P naught, right? So now again, you will just have to put together what you already know. That's all. So so what do you know? You know what is the probability of type 1 error, right? So what will be the value of alpha? So probability. So it's the probability under H naught of rejecting H naught, right? This is a type 1 error, right? So what is this? So when okay. So H naught is basically saying, so maybe I'll write it here. So probability. So H naught basic. What is H naught? H naught is basically saying that P is equal to half, right? So P is equal to half, and you want to reject H naught. So when will you reject H naught? If phi of S is greater than zero, right? When is phi of S greater than zero? Well, if it is phi of S is equal to one or phi of S is equal to P naught, right? So that means this is phi of S is equal to 1 or P naught, right? This is what it is. Okay. Okay. So, so what is this thing? Right. So this thing will become so phi. This is so this will be what summation of phi of s into probability under h naught of phi of s. So it's like expected value of phi of s, right? That you get. That what will this be equal to? So phi of s can either be 1 or p naught. So if it is 1, then you have to find the probability under h naught of phi of s equal to 1 plus if it is equal to p naught, then you have to find the probability under h naught that phi of s is equal to p naught. What will this thing be? This thing will be 1 into under h naught. What is the probability that phi of s is equal to 1? Phi of s is equal to 1 if s is equal to 0 or s is equal to 4, right? So uh, this is basically probability under p is equal to half, right? S equal to 0 or s equal to 4 plus p naught into probability under p is equal to half into s equal to 1 or s equal to 3, right? Now we know that s is binomial random variable with this parameter, right? That we know. So what will that become? So this is basically probability of s is equal to 0 plus probability of s equal to 4, right? All of this under p equal to half, p equal to half plus p naught times probability p under p equal to half of s is equal to 1 plus probability of p equal to half into s is equal to 3, right? Now what will this value become? So under s is equal to 0, so this will become 4 4c0, right? 4c0 half raised to 0 0 successes and half raised to other rest of the time you are getting failure. So that is this is what this thing will be. Then plus probability of S is equal to 4. Then that is 4C4, right? All of the time you are getting success. So half raised to 4 and 1 minus half is again half raised to 0. So this thing is here plus P naught into uh, S is equal to 1, right? So it's like 4C1, right? You are getting one success. So half raised to 1 and half raised to 3. Someone is trying to join. I don't know. Well, okay, anyway. So, and for let's see what is the probability of s equal to 3. So it's 4c3 half raised to 3 half raised to 1, and that's all right. This is all the terms. So what will this, the first term, what will it become? So this will become simply 1, right? So 1 by 2 raised to 4, that is 1 by 16, right? Similarly, this thing again will become 1. This is 1 by 16. This is 1. So 1 by 16 plus P naught times. So what is 4c1? 4c1 is 4, right? By 2 raised to 4, which is 16, plus 4c3 is again 4 by 2 raised to 4, which is 16. So now just add these things, right? So this will become 1 by 16 plus 1 by 16 is 1 by 8 plus so 2 times 4 by 16, right? So this will become 4 by 8, 4 P naught by 8. And this thing we know what is the value of alpha that is given to us. That was given to us to be 0.25, right? Which is equal to 1 by 4 to 2. You can cancel these things. So cancel this with this. This becomes 2 P naught is equal to 1 minus half, which is again half. This implies that P naught is equal to 1 by 4. Okay. I mean, it was a simple question only, but yeah, just a little bit of calculation that was involved. That's all, right? So this was the third question, right? Moving on, which question should I take next? Hmm. Okay, so let us do this question. Just a second. 435. I don't know. Someone is trying to, re repeatedly come inside and then go outside. I don't know what is happening. Okay, okay. So let's solve this question then. Okay, so this will be the fourth question, right? The fourth question is so you have some samples x1, x2 till x5, which are sampled from binomial 1 comma p. Okay, where p is between 0 and 1. Okay, so and now there are two hypotheses. What h naught is a null hypothesis which says that p is equal to 3 by 4, and there is a alternate hypothesis h1 which says that p is equal to 4 by 5. Okay, and the test here is reject h naught if summation xi, I goes from 1 to 5. This is if this is greater than 3, then you can reject h naught, is what it is saying. Okay. And then it is tell then it is given to you that the size alpha is basically your size, okay, and beta is basically your power, okay. And the question that is asked to you is what is the value of alpha plus beta? This is the question. So how will you solve this? Again, like it's simple, right? So since all xi's are sampled from binomial 1 comma p, right? So what will be the summation xi I equal to 1 to 5? Let's call this S. What will this have? What will be this distribution? Binomial 1 plus 1 plus 1 till 5 times, right? So it will be 5 comma p. Okay. This is your like this is your test function, right? Test statistic, so to say. This has the distribution binomial 5 comma p. Now alpha is your size, right? So it's basically again like it's like type 1 error only. So alpha is probability under h naught, right? Summation xi is greater than 3, I going from 1 to 5. What will this probability be? So this is probability. So if h naught, if we are assuming h naught, then p is equal to 3 by 4 actually, right? And summation xi I going from 1 to 5 greater than 3. So xi is now this thing is equal to s, and xi can act. So if s has to be greater than 3, then it has to either be equal to 4 or 5, right? Since this belongs to binomial 5 comma p, right? So this will become 5c4, right? 5c4 p raised to 4. Now p is 3 by 4, right? So 3 by 4 raised to 4, and 1 minus p is 1 by 4 raised to 1, right? Plus 5c5 into 3 by 4, 3 by 4 raised to 5, and the other term will be 1 simply. So this thing, what is this thing? So 5c4 is 5 into 3 raised to 4 by 4 raised to 5 plus 5c5 is 1 into 3 raised to 5 by 4 raised to 5. Right? What will this thing become? Okay. Uh, okay. Don't even know how to calculate this. This will become 3 raised to 4 comes out 5 plus 3 by 4 raised to 5. This thing becomes 5 plus 3 is 8. 3 raised to 4 into 2 by 4 into 4 raised to 4 into 4 into 4 raised to 3. Let's write it like this. So 2 2s are and 3 raised to 4 is what? 81 by 4 square. 4 square is 16. 16 plus 64, 2s are 128. Right. So this is your alpha, right? This is your alpha. And what is the power? Power is beta, right? So beta is basically what was the power? The power is basically what is the under h1, right? You look at h1 and the probability of rejecting the null hypothesis, right? So xi greater than 3, I going from 1 to 5. This is probability under p is equal to what? P should be equal to 3 by 5, right? Summation xi greater than 3. Now doing the same thing, right? So 5, 3, 4, 4. So what was that? H1 was it's a 4 by 5. Okay, sorry. This is not 3 by 5, it's 4 by 5. 4 by 5 raised to 4 times 1 by 5 plus 5 C5 4 by 5 raised to 5. Right? So a simple thing. What will this become? 5 into 4 raised to 4 by 5 raised to 5 plus 1 into 4 raised to 5, 5 raised to 5. This thing will become 4 raised to 4 will come out 5 plus 4 by 5 raised to 5. This thing is looking weird. So 5 plus 4, 9 times 4 raised to 4 by 5 raised to 5. And I don't think that is simplifiable. I think this comes out to be 0.737, something like that. Okay. And so this is the value of beta, basically. And this was the value of alpha. And then you can find out what is the value of alpha plus beta, right? Use your calculators. Comes out to be 1.37. Okay. This is your answer. Okay. So this was the fourth question. So now let's solve one last problem on Neyman Pearson, right? Uh, which question should I take? Yeah, this one is good enough. Right. Hmm. Yeah, I think this one question as well. Okay, so maybe I'll solve two questions. Let's see. This is the fifth question. This question also looks good. So I will solve this one and then I will solve one on naming Pearson and then we'll end. So you have n samples, x1 till xn, and all of them are sampled from normal mu comma 1. Okay, so the mean parameter is unknown, right? Uh, okay. Uh, right. So against, okay, now you have two hypotheses, H naught, which says that mu is equal to 0, and there's H1, which says that mu is equal to 2. And the critical region is given by x bar, which is equal to 1 by n summation xi equal to 1 to n greater than half. So if x bar is greater than half, then you reject the null hypothesis, else you accept it. Okay. So then the question is, what is the minimum value of n, right? The number of sample, so that probability of type 1 error is less than or equal to 0.05, right? So here the question is bit like it's not straightforward. It is basically asking you what is the minimum number of sample n that you should take so that the probability of type 1 error is less than or equal to 0.05. Okay, so how will you solve this? Simple. I mean, you just have to keep in mind the basic definition, right? So what is the probability of type 1 error? This has to be less than equal to 0.05. Okay, this implies that probability under h naught, right? And x bar, when will you reject the null hypothesis if x bar is greater than half, right? This has to be less than 0.05, right? This implies that probability under mu is equal to 0, because that was your null hypothesis, right? X bar minus 0 by, what is the variance? 1 by n, right? So 1 by root n. This thing should be greater than root n by 2. Just multiplying both sides by root n. That's all. This has to be less than equal to 0.05. Okay. Now this thing, just, I mean, if it clicked, this is your basic shifting and scaling, so that this becomes your standard normal, right? Probability that z is greater than root n by 2, less than equal to 0.05, right? Now, so now you can use your table, right? The Gaussian integral table, to conclude that root n by 2, for this condition to satisfy, has to be what? Greater than equal to 1.64, and this would lead to n to be equal to n to be greater than equal to 10.75. So if n has to be greater than 10.75, now 10.75 is a, like a decimal, right? It's a fraction. Number of samples cannot be fraction. So what is the closest natural number to this greater than 10.75? This means that n has to be equal to 11. It's 11. So I thought that this is a interesting question to solve. So yeah, this was one question. Then let's solve last question on Nim and Pearson, right? Okay. So now, so you are given again x1 till xn, right? A random samples. They are coming from a density function f of x, right? Which is what? Which is equal. So it's a exponential distribution basically. Lambda e raised to minus lambda x. If x is greater than 0, it is 0 otherwise. Okay. So usual lambda is greater than 0. This is your exponential distribution basically. The question is, so you have two hypotheses now, right? One is h naught, which says that lambda is equal to half, and there is h1, which says that lambda is equal to 1 by 4. Okay, these are your two hypotheses, and this is at level alpha. Okay, so the level is now already given to you. So basically it is saying that the probability of type 1 error is alpha, and under in this level you have two hypotheses, h naught and h1. Now you have to find out the expression for the most powerful test that exists. Okay, so most powerful test, what is it? Okay, okay. So so for that you need to first find out the joint distribution of x1 till xn, right? So what will be the f of x1 till xn? Now remember x1, these are all IID by the way. So this will be simply product of each of the densities, right? So this will simply be product of lambda e raised to minus lambda xi, right? Which is I equal to 1 to n, right? Because they are IID simply. That is equal to what? This will become lambda raised to n e raised to minus lambda times summation xi, right? I going from 1 to n. So this is like the joint distribution. Therefore, for lambda equal to half, what will be your the distribution of the null hypothesis, distribution under the null hypothesis, that will be simply, you just substitute lambda to be half here, half raised to n, e raised to minus half summation xi, I equal to 1 to n. Okay. And similarly, under lambda equal to 1 by 4, what will be f what will be the joint distribution? X1 till xn. This will be 1 by 4 raised to n e raised to minus 1 by 4 summation xi I equal to 1 to n. Okay. Now, now you have everything that you need, right? Now you can use your Layman Pearson lemma, right? By this lemma, what can you say? The most powerful test at level alpha is given by what? Simply just check the likelihood, right? So, so it will be reject H naught if the likelihood ratios are greater than some a scalar, right? So if f1 of x1 till xn by f naught of x1 till xn, this thing is greater than k. Okay. Uh, where how will you determine this k? Remember that k is determined by this thing. You see probability where k is determined by this thing. Probability under h naught f1 of x1 till xn by f naught of x1 till xn. This thing greater than k. This thing is alpha. So this is the level, right? So what will this thing become now? So this is how you like find k, but you have to simplify this further, right? So what will this be? So what is f1 by f naught? So f1 is, remember, this thing, and f naught is this thing. So just I will write it down. So maybe for brevity I will just write f1 by f naught. This thing is equal to f1 was 1 by 4, right? So 1 by 4 raised to n, right? E raised to minus 1 by 4 summation xi equal to 1 to n upon 1 by 2, right? Yeah. 1 by 2 raised to n, e raised to minus 1 by 2 summation, sorry, summation xi I equal to 1 to n, right? This thing, what will this thing become? Yeah. Uh, so this will become 2 by 4 raised to n, right? This thing, e raised to what? Minus, uh, so if I call this thing as s, right? So it's e raised to s by 4 plus s by 2, right? This will become 1 by 2 raised to n, right? And 1 by 2 raised to n, and s by 2 minus s by 4 is s by 4, e raised to s by 4. This thing should be greater than some k, right? So it should be greater than some k. And so what can I do? Take this thing here, right? So e raised to s by 4 has to be greater than 2 raised to n times k. This implies take log both the sides. So s by 4 should be greater than what? N log 2 plus log k. This implies that s should be greater than 4n ln 2 plus ln k. Let's call this a new constant c, right? So this implies that s, which is equal to summation I equal to 1 to n xi, should be greater than some c. So then reject h naught. So this c you can find out by if you know this k, right? Since alpha was not given to us, we cannot find this thing exactly, but you can write it in terms of this thing. Sorry. So this is what the expression for the most powerful test will look like. Okay. So yeah. So I think this was the last question that I had. Okay. So yeah, I think yeah. almost five. Uh, any questions? I don't have a question on Poisson distribution actually. I just had these questions, so I solved all of them. I don't have any extra question, but if you have any doubt, I can maybe answer those. Okay. Uh, okay. So just a second. Yeah. So if there are no doubts, then maybe I will just stop. Yeah. Sure. I will stop presenting and leave this thing. Leave from this device. So okay. So thank you for joining and yeah. Uh, maybe see you in the next problem solving session. So I think there are two more sessions left. One will be for the next week's, so like week 12's problems, and the last one will be an additional doubt solving, this general doubt solving, and some maybe some more problem solving. And then we this course will end. Okay. So okay. So see you next time. Have a nice day. Okay. Goodbye. Thank you.